Okay, we'll start on chapter 2, synthesis of process diagram. In chapter 1, you have been introduced on how to design the basic process, the basic step, okay, to design a process. Okay, we have few parts, part 1, 2, 3, and 4, up to the construct the plant, construction stage, right? Now, today's class, chapter 2, you will learn about the rule of thumb for process synthesis. Few heuristics will be introduced. Okay, there are, I'm not saying few, a lot. Okay, so you should understand what are the heuristics and the hierarchy of the design process. Okay, as we recall this manufacturing of VCM, the process synthesis involve mainly 5 steps. Okay, 5 steps. Now, first one is the chemical reaction involved. Chemical reaction involved here, it includes the raw materials that you need to use. What type of raw materials that you need to use? Okay, and the reaction involved. How many steps of reaction? Whether it is a series or parallel. Okay, next step is we will look into the mixing and recycle process. Okay, how you can distribute the chemicals. Third one, focus on the separation to eliminate differences in the composition. Okay, to separate your products with the byproducts. What equipment you should use. Okay, what step you should further, you should proceed with. Okay, if vapor, how will you separate them? Whether you need to condense them first to liquid, then only separate, or you can directly, perhaps you can put. Okay, so it depends with the process. Now for number 4, temperature, pressure, and phase change. This one involves the heat transfer. The heat exchanger network, okay, the utilities. Okay, then number 5 is the in-task integration. Okay, this is the heat exchanger network. Number 4, just now the utility, the pump, the compressor, cooler. Okay. Now these are the 5 process operations in process synthesis. Each of these process operation, it has their own heuristics, their own step. Okay, you will see later on that many. Okay, so on the second part, we have a lot, 7. This one 3, if I'm not mistaken. Okay, so we'll go through one by one. Why do you need to understand this? Because you need to understand the importance of selecting the reaction path. Whether you need 1 reaction or 2 reaction in order to produce your product. Whether it should be in series, parallel. Okay, and try to not involve the toxic and hazardous chemicals. Or if you cannot avoid, try to reduce the presence of the hazardous chemicals. Okay, then you should be able to distribute the chemicals. What is the input, output? What is your byproduct? Okay, what is your waste? What is your inert? Okay, then be able to apply heuristics in selecting the separation process to separate liquids, vapor, or vapor liquid mixture. Okay, then be able to distribute the chemicals, whether you should use the excess reactant or not. Your inert diluents and full shots to remove the exothermic heats of reaction. Okay, this one to focus on the exothermic heats of reaction, whether you need excess of reactants or inert or anything necessary. Okay. Now, number 5 is to understand the advantages of pumping a liquid rather than compressing a vapor. Okay, so you need to consider which one is more feasible, whether to pump a liquid or compress a vapor. Let's say your product is in vapor form. So would you rather use compressor to connect to other unit op or condense it into liquid then pump it to the unit op? Okay, that one involve the costing analysis as well and also the safety analysis. Okay, we go to the first one, raw materials and the chemical reactions. Okay, to select the raw materials, when you select the raw materials and chemical reactions, you should avoid or reduce hazardous and toxic chemicals. For example, we have manufacturing of ethylene glycol, where you use ethylene react with the oxygen. Ethylene oxide is produced as the intermediate product. Okay, ethylene oxide as intermediate. This ethylene oxide is flammable, hazardous. Okay, you see here the statement. A water spill into an ethylene oxide storage tank could lead to an accident, similar to the Bhopal incident. Okay, ethylene oxide is hazardous. So when you proceed reacting ethylene with oxygen, you will have ethylene oxide as intermediate. That means in your reactor, input is ethylene and oxygen. Then you will get product is ethylene oxide. So that ethylene oxide you need to keep in storage before you react with water in order to proceed with to produce the ethylene glycol. Okay, so that ethylene oxide is hazardous. You will need to consider other pathway that can produce your ethylene glycol. Okay, so perhaps these are the alternatives. You can eliminate the storage tanks, okay, causing the intermittent interruptions when the oxidation reaction shut down. Okay, if you have shutdowns, so your ethylene oxide is still there, even though it is shut down. So eliminate the storage tank. That means perhaps the product stream from the reactor, you can directly go to another reactor instead of putting into any storage tank. Okay. Second alternative, perhaps you can use chlorine and caustic in a single reaction step to avoid the intermediate. Okay, here your ethylene react with chlorine and sodium hydroxide. Now you have ethylene glycol. Okay, where initially you consider this as your reaction. Okay, so you can alternatively use this reaction to produce the same product, less hazardous. Another alternative is, as ethylene oxide is formed, react it with carbon dioxide to form ethylene carbonate, okay, which is a less active intermediate since it is in carbonate form, and that ethylene carbonate can be stored safely and hydrolyzed to form the ethylene glycol product. Okay, so the ethylene oxide that you have react with CO2 to form the carbonate, then hydrolyze it to form ethylene glycol. The issue here is from the original reaction that perhaps you propose. Let's say you propose this reaction. You didn't find any other reaction. This is your first proposal for the reaction. But it produced ethylene oxide as the intermediate. So to reduce the toxicity, the hazardous state, this ethylene oxide, perhaps you can react with CO2 to form the carbonate, then hydrolyze to form ethylene glycol. Or alternatively, you can straight away use ethylene react with chlorine and sodium hydroxide. You can directly get ethylene glycol. This one. So that is why in your PDP1, you need to select at least 3 process synthesis, 3 process pathway. Right? Are you in that step now? So each of the synthesis, not yet. Each of the synthesis, you need to consider whether it is hazardous, toxic, not only the raw material and the product. You should also consider the intermediate that you will be producing. Okay. Now that one on the first chemical reaction. Next, after you distribution of the chemical. Okay, so the second step. Use an excess of one chemical reactant in a reaction operation to completely consume a second valuable toxic or hazardous chemical. Okay, let's say you have toxic and hazardous reactant. One of them should be used in excess in order to reduce the toxicity and the hazardous reactant. Okay, how do you know whether it is hazardous or toxic chemical? MSDS. That's why you need to include in your report, I think, the MSDS. For your FYP also later on, each chemical you need to check the MSDS. What is MSDS? Material Safety Data Sheet. Okay. You can Google for it. Okay, for example, here we have the VCM production. Consider using excess ethylene in vinyl chloride production. Excess ethylene. Ethylene, chlorine. Okay, but here Cl2 is toxic and hazardous. Okay, so consider to use ethylene. Because why? Cl2 will be the limiting. So when you have excess of ethylene, all Cl will be consumed. All Cl will be reacted. Okay, so when you have ethylene as your excess, perhaps you can recycle that ethylene back to your feed. Okay. Heuristic 3, still on the distribution of the chemicals. When nearly pure products are required. Okay. Eliminate inert species before the reaction operations. When the separations are easily accomplished or when the catalyst is adversely affected by the inert. Okay, this one, let's say you require your highly pure product, but you have inert in your feed. So you can consider to remove the inert before the reaction. Okay, for example, over here we have impure reactant C, okay, impure feed C, which it contains inert D. Impure reactant C contains inert D. You need this C, but in the C you have inert. For example, O2 and N2. You need the oxygen, but the N2 is the inert. Okay. So decision is required whether to remove D before or after reaction 2. So C over here will go into reaction 2, feed to reaction 2. But C consists of inert D. Now you need to decide whether to remove the inert, the D, before or after the reaction. Which one is more feasible in comparison of the cost and the complexity of the process as well? Okay, ease of cost of the separation must be assessed. For exothermic reactions, the inert species absorb some of the heat generated. Okay, so somehow that inert will lower the final temperature of the reactors. Okay, so for example, taking example combustion inert in the air. Let's say D is the N2, which is more feasible to remove before the process or after the process. Okay, if before, you need to set up some unit op to separate the N2. Okay, or if you decide after, where it involves many more components that you need to consider. Okay, D in the product side, here you have E, D, perhaps some of A and C in your product stream. So if you decide to separate after the reaction, you need to consider all those components' properties. Okay, many more considerations need to be done. Otherwise, let's say your product stream is in liquid form. Nitrogen is in gas form. So you can just directly purge. Okay, so again, it is case by case. If let's say that reactant consists of inert as well, impure, not pure reactant. Because, for example, natural gas, it is not purely CH4, right? You have other type of gas as well. So, is it feasible to remove those impurities before the feed or after the feed? Get it? You just need CH4 for your reaction, but you have impurities. So, you need to consider, is it feasible to remove the impurities before or after? Okay, next one is to introduce liquid or vapor purge stream. Liquid or vapor purge stream to provide exits for species that enter process as impurities or produced by the irreversible side reactions, the byproduct. Okay, this can be applied when the species are in trace of quantities and or difficult to separate. In trace quantities means just a little amount of it, like 0.001%. Okay, for example, here we have ammonia reactor loop. Your feed is N2 and H2. In N2 stream, you have trace of argon. And H2 stream, you have trace of CH4. Okay, then mix them in a reactor, react them in a reactor. Stream over here will be in liquid or vapor. Product phase after the reactor. Product phase, liquid or vapor from this diagram. Huh? Here. At this stage. Liquid or vapor? Vapor. Why you say vapor? Yes, because clearly you can see condenser over here. Okay, product stream right after the reactor. It is in vapor form. Because here we can clearly the condenser. That's why we can say it is vapor. Okay, now the product which consists of ammonia and perhaps traces of argon and CH4. Okay, the impurities. So they condense, turn from vapor to liquid, then go for flash vessel. The gases, which is argon and methane, purge out. That means argon and methane is not liquefied. They are still in their gas form. Condense over here, we condense only on the ammonia. So you should look into the properties of the, what is the temperature to condense the ammonia and the gases. So you should set the temperature for the condenser to only condense the ammonia. Okay. Now, once the ammonia condensed, turn into liquid form, the rest still in the vapor form, the gas form. So that's why they use the flash vessel where it will purge out the gases, which is the impurities, the argon and the methane. Okay, the purge on top over here, you can see they split purge and recycle back to the reactor. Okay, here, if the gas still contain N2 and H2, then it is feasible to be recycled back. Okay, if at high, still at high amount. Okay, can not fixed, it's still case to case basis. Yes. You mean whether they are the same or different? The numbering, they can change as you go through into the process. But as in for the notes over here, just let it fix up. Just fix the number. Once you run your process, PDP, everything, perhaps you no need to follow the heuristic. Okay, heuristic 5, which is do not purge valuable species or species that are toxic and hazardous, even in small concentration. Okay, for toxic and hazardous component, even though it is in very small percentage, you cannot purge them because it will impact the air, okay, the environment. So what you should do, perhaps you can add separators to recover the valuable species or add reactors to eliminate the toxic and hazardous species. Okay, for example, here in combustion, engine combustion, you have fuel and air in excess. Okay, so goes into combustion chamber. Incomplete combustion where you have CO and NOx. Then from here, you cannot purge this thing. Okay, you cannot purge the NOx CO because it is hazardous gas. What you should do, you should convert them into less hazardous compound. Okay, who's driving the car? Catalytic converter is in the exhaust, before the exhaust part. Okay. Okay, 6. A lot, huh? Just follow me closely. Byproducts that are produced in reversible reaction in small quantities are usually not covered in separators or purge. Instead, recycle to extinction. Okay, this statement means when you have a reversible process, so at one state, it will become equilibrium. Okay, it will achieve the steady state by recycling the product species without removing them. So once you recycle, the component will be consumed by the reaction, used by the reaction until it extinct. Okay, until the byproduct is fully consumed. But it will not happen if you have irreversible process. That small quantity byproduct must be purged. Okay, otherwise it will build up in the process continuously. Okay, either recycle or purge. Sorry? Yes, you can purge them if it is not hazardous. Okay, for heuristic 7, for computing series of parallel reactions, okay, where it involves the adjustment of the temperature, pressure, and the catalyst to obtain high yields of desired product. Okay, so here you will need to check on the kinetics data and their properties. For example, here, manufacture of allyl chloride. This is your product, allyl chloride. There are few reactions in the series of parallel. Okay, you can see over here, reaction 1, reaction 2, reaction 3. So there are few reactions, series, parallel, or series parallel. The B is your product, means the allyl chloride. So this allyl chloride can be produced either in series, parallel, or mixed. So which one to choose? You should compare the rate constant, the temperature. Compare the temperature. Okay, if it is temperature depending. So for example here, it depends on the temperature to produce higher yield. So check on the properties, find the cross point, where is the suitable temperature in order for you to achieve higher yield. Okay, in this case, considering root 1, 2, and 3, okay, according to this figure, the suitable temperature falls between this temperature. Okay, this red arrow. Okay, so at this temperature, it has the desired reaction yield. Okay. For reversible reaction, you can consider conducting them in a separation device that capable to remove the products. Okay, hence driving the reactions to the right. For example, here we have a manufacture of methyl acetate with reactive distillation. Okay, reactive distillation. So there are many types of distillation column. This reactive distillation, it involves reaction and separation in one unit, where methanol, which is more volatile than acetic acid. Okay, this is your input of methanol, acetic acid. Methanol is more volatile. So the feed stream is put at the bottom, where we know in distillation, bottom here, high temperature, correct? Correct. High temperature. So when methanol enters at bottom over here, it is more volatile compared to the acetic acid. So it will it will turn to vapor. Concentrate in vapor phase and contacts with acetic acid. So it will vaporize, then contact with, it will vaporize, then it will move upward because it is more volatile, right? So it will move upward, then while moving upward, it will react with the acetic acid in the reaction zone over here. So in this reaction zone, methyl acetate forms. Then it concentrates in vapor form and leaves the tower in pure distillate. Okay, again, methanol fit in at the bottom part because it is more volatile. Once it enters, it will move upward, then react with acetic acid in the reaction zone to form methyl acetate. Okay, so as it goes up here, it will be purified. The water product concentrates in liquid form and it will go to the bottom product. Okay, so later in your PDP, you should know what type of distillation column that you will use. Okay, you want 5 minutes break? Okay, let's take 5 minutes break. Where's the attendant? Attendance. Okay, let's start. Let's review. Now, after you have your product, your raw material, then go into reactor, then you have your product. Okay, the product stream, in actual, you will have mixtures of components. Your byproduct, your main product, byproduct, your waste. So you will need to separate them in order to get only your main product. Okay, now that's where the separations come in. So you should consider which separation system to use, what unit ought to use. Okay, separate liquid mixtures, using distillation, tripping, or other type of distillation. Okay, liquid extraction, crystallization, and or adsorption. So which unit op is suitable to your process? You should consider that. This is the common separation process for liquid. Okay, if you have vapor mixtures, try to condense or partially condense. Similar like the ammonia production just now. Okay, partial condense. Okay, attempt to condense or partial condense vapor mixtures with cooling water or refrigerant. Okay, then after you have the phase change, which change to liquid, then use heuristic 9, which is the distillation, liquid extraction, adsorption unit op. Okay, here is your reactor. Stream from the reactor is in vapor form. Okay, it's in vapor form. So consider to condense, fully condense or partially condense your mixtures, your vapor mixtures. Okay, then split them in order for you to recover your main product. Let's say your product is in liquid form, so split them, flash column, separate liquid and vapor. So you have your liquid over here. Vapor on top. So on top over here, you recover the vapor product. Okay, the point here, attempt condense, fully condense or partially condense for your vapor mixture product. Okay. But if your product, you need it in gas form, should you consider for condensation process? Huh? Depends. Why?
gases like CO2 if you want to store it, then it is.
Mm-hmm.
But if not, then most of the time we don't put that.
Correct. If your product you require in gas form, so the condensation process, it depends to based to case basis. Let's say, for example, like Haliza mentioned, your CO2. For storage, we need quite a volume to store gas product. Otherwise, you just turn it into liquid form, liquid nitrogen, liquid CO2. Okay, so it depends, case to case basis. If your product is, let's say, methane gas form, okay, so you don't need to condense into liquid form. Okay. So this step, it is not compulsory. It still depends to your process. Now the third one, separate vapor mixtures using partial condenser or cryogenic distillation, adsorption, membrane separation or sublimation. Okay, few other unit of. Here is your reactor, then liquid. Sorry, reactor, you have liquid and vapor. So condense them. You can use condenser or cryogenic distillation. Then you can split them where you have mixture of phases over here. If you have mixture of phases, split them. Liquid go to the liquid separation system. Then vapor go to the vapor recovery system. Okay, basically the separation. Okay, basically the separation system, what I can conclude is, if your product is in liquid, okay, your product, it can be in liquid or vapor, those two only. Solid, different story. Okay, liquid and vapor. So if liquid, you can use distillation, stripping, other type of distillation, crystallization, everything. Straightforward, liquid. Okay, but if you have vapor as your in your product stream, you should consider whether to fully condense or partially condense, or both not required. So it depends to your end product as well. Your product is liquid or gas? Both. Yes. Liquid on bottom, gas on top. Like for ammonia just now, we have ammonia in liquid form. Then all the gases, the impurities like nitrogen, argon in gas form. So that one is partially condensation, partial condenser. Yes, mixture. So that's why for the condensation temperature, you will need to check on what temperature do you require to condense only ammonia, for example. Okay. Like boiling point lah. There are specific temperature for specific components, right? You need. Okay, any questions so far? Yeah, perhaps. You are giving me idea. I can ask question by giving you case study, or I give you PFD. PFD, right? So let's say not PFD, like BFD, like this. Okay, for example, right here, number 3. I give the BFD, then perhaps I would ask what unit operation that you require for the separation of the liquid. Then do you require any condensation process? Okay, something like that. Or I can ask directly to list what are the heuristic of separation. Something like that. Okay. If you have, let's say I give a situation where you need your product in liquid form, but your reactor effluent is in vapor form. So how should you proceed? It depends to the properties of the product as well. Okay, Anna? Okay, here to summarize for separation. Reactor exit is liquid. Okay, straightforward. We can use the distillation, adsorption, the membrane, everything. If the reactor exit is in vapor form, you can consider partial or fully condensed, then separate them. If it is partial condensed, you need to separate them again for the vapor recovery and liquid separation. Okay, so this one, if reactor exit is vapor and liquid mixture. For the vapor here, you condense into liquid form, then combine with the liquid stream. Then from this liquid stream, perhaps you proceed with the separation. What unit op that is suitable for that? Okay. And then for the vapor on top here, you need to recover. What unit op is suitable to recover? Okay, so you need to identify those things. Okay, for the purge over here, if it consists hazardous pollutants, hazardous components, so is it suitable to purge or not? So you need to consider all those things. Okay. Okay, let me check. Let me share with you the previous test question. Wait, I share with you this one. This one is final exam. Okay, final exam. This question, you need to illustrate the process flow diagram. Okay, given this one, so you need to illustrate the process flow diagram. This one in chapter 1. Okay, for chapter 2, the heuristic, this is the question. Elaborate 3 heuristics for separations and 1 chemical distribution heuristic. Chemical distribution, we have 7, so at least 1. Okay, and separation, 3, only the 3. Liquid, vapor, vapor mixture. Okay, then here, once you elaborate the heuristic, you need to construct the new process flow diagram by including the heuristic elaborated in here. Okay, this one is according to this. So after here, transesterification, biodiesel in liquid form. So how do you separate the product, the product and the byproduct? So to answer that one, you need to propose the new BFD by including the separation at. Yes. Yeah. Okay, crude glycerin, then refine glycerin refining. What unit ought that you need over here? Okay, methanol recovery, whether it is in gas form or liquid form. So what do you need over here? Okay, from this trans esterification, the input is methanol plus catalyst. Theoretically, you will have methanol and catalyst release over here in either one of the stream, right? So how you can propose how you can separate them to get only your pure products. Here, let's say here, crude biodiesel is your product, your main product, right? So it must have some traces of methanol and catalyst. So how can you separate them? Then how can you refine them?
But then in terms of catalyst, which is solid, and you should decide to separate the catalyst out.
With the pressure?
If the catalyst is solid,
Uh-huh.
then maybe you cycle.
Cyclone?
Yes. But then.
No. Yeah.
But you won't ask about it. Okay.
Solid, not focusing too much on solid. Okay. For the test, the midterm covered only CLO1. Okay, this is the midterm question last time. I give statements, then you need to construct the process flow diagram based on this statement. So here it mentioned the input is H2 and N2. Product is NH2. Here you mentioned also recycled gas and purge gas. So you need to know where to put the purge gas stream, where is the recycle stream. Based on this statement, you need to construct the process flow diagram. Okay. This is the test last time. My part is this one only, but this topic we haven't covered yet. Okay, later I'll share when the time comes. Okay, I think I will stop over here. Heat transfer we continue tomorrow. Tomorrow dual mode, eh? I still come to the class if you want to come. Going back already. Okay, for those who are going back already, drive safe. Enjoy your holiday. Okay.